500 meters above the ground. That is not the height of the bridge deck, that is the height of the valley it crosses. The Beipanjiang Bridge in China holds the record, 565 meters from the road surface to the river below. Higher than the Empire State Building, higher than any bridge ever built in human history. It took 4 years to construct, it cost nearly $1 billion. And at multiple points during construction, engineers privately questioned whether it could be finished at all. The winds at that altitude do not behave like wind at ground level. The geology on both sides of the valley is not uniform. The cable system that holds the deck in position operates under forces that no textbook fully prepares you for. 13 workers died during construction. The project ran over budget, over schedule, over the limits of what the engineering team originally believed was possible. The bridge stands today. It is real, it is open. But the story of how it got there and what it cost the people who built it has never been told in full. Until now. The problem begins with geography. Southwest China, the provinces of Guizhou and Yunnan, is one of the most mountainous regions on Earth. Peaks rise sharply from river valleys. Gorges cut thousands of meters deep into the plateau. The terrain looks beautiful from above. From the ground, it is a logistical nightmare. For decades, the communities on either side of the Beipanjiang River Gorge are effectively separated. The road distance between 2 points that sit less than 1,500 meters apart as the crow flies is over 5 hours by vehicle. Goods travel the long way around. Workers travel the long way around. Emergency services travel the long way around. The economic cost is enormous and largely invisible, calculated not in single dramatic events, but in 10,000 daily inefficiencies accumulating across generations. Chinese infrastructure planners identify the gorge as a critical bottleneck in the regional development strategy for Guizhou Province, one of the poorest provinces in the country. A bridge across the Beipanjiang Gorge is not a vanity project, it is an economic lifeline. The engineering brief is straightforward in concept: connect the two sides, carry a highway, handle the traffic loads of a modern expressway, survive the wind, the seismic activity, and the weather of a high-altitude river gorge environment. In practice, the brief describes one of the most complex bridge engineering challenges ever formally tendered. The crossing point is selected after 3 years of survey work. The gorge is at its narrowest here, 1,440 meters between anchor points. But narrowest does not mean easiest. The rock faces on both sides rise nearly vertically. The valley floor is 565 meters below the planned deck level. A suspension bridge is the only viable structural solution. A cable-stayed bridge cannot span this distance at this height with adequate stiffness. A conventional beam bridge is structurally impossible at this scale. The suspension bridge design is approved. Engineers look at the numbers and feel two things simultaneously: pride and a quiet, specific fear. Getting equipment to the site is the first engineering problem. There are no roads to the construction zone, not real ones. Provisional access tracks must be carved into the gorge walls before a single structural element can be delivered. This process alone takes 11 months. Drilling rigs are lowered by crane to positions on the rock face. Workers abseil to locations where no road can reach. In some sections, the only way to place a survey instrument is to hang it from a rope anchored 50 meters above. This is before construction officially begins. When it does begin, the scale is immediate. The two main towers, the vertical columns from which the suspension cables will hang, must be founded in rock. Not soil, not fill. Solid, load-bearing rock capable of resisting forces measured in tens of thousands of tons. Core drilling reveals the rock on the Guizhou side is excellent. Dense, competent limestone extending deep below the surface. The Yunnan side is different. The rock is sound at depth, but the upper layers, the first 40 meters, show weathering and fracturing from centuries of freeze-thaw cycles at altitude. The foundation design for the Yunnan Tower must go deeper than planned, significantly deeper. The foundation excavation on the Yunnan side requires controlled blasting in a sequence of over 200 individual detonations. Each blast is calculated to remove rock without transmitting shock waves that could disturb the Guizhou side foundation work happening simultaneously across the gorge. The coordination required is extraordinary. Both towers begin rising from their foundations in the same construction season. The Guizhou Tower climbs faster, better rock, simpler logistics. The Yunnan Tower climbs more slowly, its foundation work still being refined as the lower sections of the shaft are built above it. At 150 meters of tower height, engineers conduct the first full structural survey of both shafts. The Guizhou Tower is within tolerance on every measurement. The Yunnan Tower has a lean, Not visible to the naked eye. Not dramatic. 2.3 centimeters of horizontal deviation from true vertical across 150 meters of concrete shaft. The project specification allows a maximum deviation of 1.5 centimeters. The Yunnan Tower is already out of tolerance, and it is not yet half its final height. 2.3 centimeters sounds trivial. In a suspension bridge tower that will eventually stand 269 meters tall and carry cable loads exceeding 40,000 tons, it is not trivial at all. The lean must be corrected before the tower can continue rising. If it is not, every additional meter of height amplifies the deviation. By the time the tower reaches full height, a 2-centimeter lean at midpoint could translate to geometric errors at the cable saddle positions that make it impossible to achieve the correct cable geometry across the span. The cable geometry is everything in a suspension bridge. Get it wrong and the deck hangs unevenly. An unevenly hanging deck develops stress concentrations. Stress concentrations cause fatigue cracking. Fatigue cracking in a bridge deck 500 meters above a river gorge is not a problem that announces itself gently. Engineers halt vertical construction on the Yunnan Tower. A correction strategy is developed over 6 weeks. The solution is precise and slow. Hydraulic jacks are installed at specific points within the tower shaft. Over a period of 3 months, the jacks apply controlled lateral pressure, measured in fractions of a millimeter per day, to incrementally push the tower back toward true vertical. The process works. The tower returns to within tolerance. But 3 months of corrective work on one tower means 3 months where the entire bridge program waits. The project falls behind schedule for the first time. Then the cable works begin, and a different problem surfaces immediately. The main suspension cables must be spun across the gorge from anchor to anchor, a process called aerial spinning, where thousands of individual wire strands are carried back and forth across the gap and bundled into the final cable. The equipment that does this, a spinning wheel, travels on a temporary tramway stretched across the full crossing. Setting up the tramway requires a pilot rope to be transferred from one side of the gorge to the other. At 500 meters of altitude, with nothing below but the river, a helicopter carries the pilot rope across. The first attempt fails. The wind at gorge level is predictable. The wind at deck altitude, exposed to the full sweep of the plateau, is not. The helicopter is pushed off course. The rope drops short. The second attempt, 3 days later, succeeds. But the wind data collected during those attempts reveals something the meteorological studies did not fully capture. The gorge creates an acceleration effect. Wind funnels through the valley and speeds up as it rises. At deck level, wind speeds regularly exceed the parameters used in the aerodynamic design of the bridge deck. The deck design must be reviewed. The aerodynamic review takes 4 months. Wind tunnel testing is conducted at a university laboratory using a scale model of the deck cross-section. The results confirm the field data. At the wind speeds regularly recorded at deck level, the original deck profile generates a flutter response, a dangerous oscillation where wind energy feeds into the structure's natural frequency. Flutter killed the Tacoma Narrows Bridge in 1940. Engineers do not need reminding of this. The deck cross-section must be redesigned. The original closed box girder profile is modified. Edge fairings are added. Ventilation slots are cut into the deck soffit. The overall aerodynamic shape is refined until wind tunnel testing shows stable behavior across all recorded wind speed ranges. The redesign adds $14 million to the project cost. It also means the steel fabrication order for the deck sections must be partially reissued. 144 deck segments have already been fabricated to the original specification. 61 of them require modification before they can be installed. The modification work is done at the fabrication yard, not on site. Each segment must be transported back, modified, inspected, and returned. The project is now 18 months behind schedule. The budget has increased by 30% above the original figure. Government infrastructure officials fly to the site for the first time since groundbreaking. They do not hold a press conference. They review documents, ask questions, and leave. 2 weeks later, a new project oversight committee is formally established. It has authority to approve or reject all further design changes. Every variation that affects cost or schedule must now pass through this committee before implementation. The committee meets once per month. In a project where engineering decisions sometimes need to be made within hours, a monthly approval cycle creates its own delays. A stability monitoring system detects unexpected movement in the Yunnan anchor block, the massive concrete foundation that holds one end of the main suspension cables in the rock face. The movement is small, 3 millimeters over 40 days. 3 millimeters is enough to require investigation. Boreholes are drilled around the anchor block. Ground monitoring sensors are installed. The investigation finds a water infiltration path, rainwater entering through a surface crack in the rock above the anchor, tracking down through a natural fissure and accumulating behind the anchor block foundation. Water pressure behind an anchor block reduces the effective friction holding it in place. The anchor block drainage system must be completely redesigned and installed under emergency conditions while cable spinning, which depends on the anchor holding position, continues above. The budget crosses $600 million. Then a cable band fails. Cable bands are the steel clamps that grip the main suspension cables at precise intervals and connect the vertical hanger cables that support the deck below. Each one is machined to exact tolerances. Each one is torqued to a specified clamping force using calibrated equipment. During a routine inspection of the completed cable band installations on the main span, an engineer notices that one band on the Yunnan side shows visible gap between its two halves at one edge. A gap means the clamping force is insufficient. Insufficient clamping means the band can slip along the cable under load. A slipping cable band changes the hanger geometry. Changed hanger geometry changes the deck load distribution. In a structure of this complexity, one slipping component creates a cascade of secondary effects through the entire system. All cable band installations are immediately suspended. Every installed band, 172 of them, is re-inspected and retorqued. 27 bands across both cables show insufficient clamping force. The root cause is traced to a calibration error in the torque equipment used by one installation crew. The equipment was reading correctly. The calibration certificate was not current. The equipment had drifted out of calibration and nobody had caught it. 27 cable bands must be loosened, cleaned, inspected for surface damage, and reinstalled to correct torque values. The process takes 11 weeks. During those 11 weeks, no deck segments can be installed. The deck erection crane, a massive piece of equipment that cost millions to mobilize to this location, sits idle. Regional media begins covering the project for the first time. Not the engineering, the delays, the cost. The workers who have now been on site for over 3 years with the end nowhere in sight. A local journalist publishes photographs of the idle crane and the unfinished deck. The story runs nationally. Questions reach Parliament. The Oversight Committee chair gives a press statement. He says the project is progressing. He says structural integrity is being maintained at every stage. He says the opening date is under review. He does not give a new opening date. After the cable band crisis, the project leadership makes a decision that changes the atmosphere on site. No more internal management of problems. Every technical issue, regardless of size, is now reported to the Oversight Committee within 48 hours. Every corrective action is documented publicly. Every schedule impact is acknowledged in writing before work resumes. It is a painful policy. It means admitting problems that previous project cultures would have quietly resolved and never reported. But it means nothing goes undetected long enough to become a crisis. Deck installation resumes. The redesigned deck segments, aerodynamically refined, modified at the fabrication yard, arrive on site and begin going in. The installation process is meticulous. Each segment is lifted from a platform on the gorge wall, carried out over the void by the deck erection crane, and connected to the hanger cables below. At 500 meters above the river, this operation is conducted in wind conditions that would stop work on any other construction site in the world. Work continues here because the project has already lost too much time to stop for anything short of a direct safety threat. The wind monitoring system guides the work. When gusts exceed the safe operating threshold for the crane, operations pause. When conditions ease, they resume. On some days, productive installation happens in windows of 40 minutes between gusts. Progress is real, but slow. The deck closes, both halves meeting at midspan, 7 months behind the revised schedule. The closure is a significant moment. Engineers on both sides of the gorge can see each other across a connection that did not exist 4 years ago. But the bridge is not finished. The road surface, the barrier systems, the lighting, the drainage, the instrumentation network, all of it must still be installed and tested. And the instrumentation reveals a new concern. Sensors embedded in the Yunnan Tower during construction are showing stress readings in the upper shaft that sit at the high end of the predicted range. Not outside specification, not dangerous, but consistently at the upper boundary under thermal loading. when the sun heats the tower face unevenly and causes differential expansion. The design team models the readings. They conclude the tower is behaving within acceptable parameters. A second independent team is asked to review the same data. Their conclusion is more cautious. They recommend additional monitoring for a minimum of 12 months before the bridge opens to full traffic loading. The opening is delayed again. The Beipanjiang Bridge opens. There is a ceremony. There are speeches. Cars cross for the first time. The journey that once took 5 hours now takes minutes. The photographs are extraordinary. A bridge emerging from cloud. A road hanging in sky. An engineering achievement that looks, from a distance, like it was always inevitable. It was not inevitable. 13 people died building it. The budget ran hundreds of millions over its original figure. The schedule extended by years. The tower leaned. The cables were misinstalled. The deck design had to be reborn from its aerodynamic failure. The anchor block nearly moved. At every stage, something went wrong that the plan did not anticipate. At every stage, engineers found a way through. But the bridge now carries a weight that does not appear in any structural calculation. The Yunnan Tower stress readings are still being monitored. Monthly reports go to the Oversight Committee. The numbers stay within range. But they stay at the high end of that range. And the engineers who built this bridge, the ones who were there for every crisis, every correction, every 11-week stoppage, they know something that the opening ceremony photographs do not show. A bridge this extreme is never fully finished. It is only continuously managed. And the question nobody asks at the ribbon cutting is the only question that actually matters. What happens the day the monitoring finds something it was not expecting?